time to confront just how strange and remarkable our galaxy truly is. The Milky Way is not simply a collection of stars scattered randomly through space. It is a dynamic, evolving system filled with phenomena that challenge our understanding of physics, time, and existence itself. What we can see with our eyes and telescopes represents only a tiny fraction of what is actually there. The rest remains hidden, invisible, detectable only through its gravitational influence on the matter we can observe. 90% of the Milky Way is composed of something we cannot see, touch, or directly measure. Scientists call it dark matter, and it remains one of the greatest mysteries in modern astrophysics. We know dark matter exists not because we have observed it directly, but because galaxies like ours behave in ways that cannot be explained by visible matter alone. Stars at the outer edges of the Milky Way orbit the galactic center far too quickly. According to the laws of gravity and the amount of visible matter we can detect, those stars should be moving much slower, or they should be flung out into intergalactic space entirely. But they are not. Something unseen is holding them in place, providing the additional gravitational pull needed to keep the galaxy intact. That something is dark matter. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way we can detect, yet it outweighs all the stars, planets, gas, and dust in the galaxy by a factor of 9 to 1. For much of human history, we did not even know that other galaxies existed. Ancient astronomers looked up and saw stars, planets, and the occasional comet, but they had no concept of the true scale of the universe. Even as recently as the early 20th century, many scientists believed that the Milky Way was the entirety of the universe. They thought that beyond our galaxy lay only empty void, an endless darkness stretching into infinity. It was not until the 1920s that this view was shattered. Astronomers discovered that the universe was far vaster than anyone had imagined. The Milky Way was not the whole cosmos. It was just one galaxy among billions, perhaps even trillions, scattered across an incomprehensibly large expanse of space and time. Within the Milky Way itself, there are stars that have existed for almost as long as the universe itself. The oldest known star in our galaxy is called the Methuselah star, named after the biblical figure renowned for his great age. This ancient sun is estimated to be approximately 13.6 billion years old, only slightly younger than the universe itself, which formed 13.8 billion years ago. The Methuselah star is a relic from the earliest generations of star formation, a survivor from an era when the galaxy was young and chaotic, still coalescing from vast clouds of primordial gas. To put this in perspective, when this star ignited, the Earth did not exist. The Sun did not exist. The solar system would not form for another 9 billion years. This single star has witnessed nearly the entire history of the cosmos. But the Milky Way is not a static object frozen in place. It is moving, and moving fast. The entire galaxy is hurtling through space at approximately 600 kilometers per second. That is over 2 million kilometers per hour. We do not feel this motion because everything around us, the Earth, the Sun, the solar system, and all the nearby stars, are moving together as part of the same galactic structure. But relative to the cosmic microwave background radiation, the afterglow of the Big Bang itself, the Milky Way is racing through the universe at breathtaking speed. This motion is driven by the gravitational pull of other massive structures in the cosmos, including the Virgo supercluster and the even larger Laniakea supercluster, vast networks of galaxies bound together by gravity. And the Milky Way is not alone in its journey. There is another galaxy on a collision course with us. The Andromeda galaxy, our nearest large galactic neighbor, is barreling toward the Milky Way at roughly 110 kilometers per second. In approximately 3.75 to 4.5 billion years, the two galaxies will collide. This will not be a sudden, violent crash like two cars smashing into each other. Galaxies are mostly empty space. The distances between individual stars are so vast that even when two galaxies merge, the stars themselves rarely collide. Instead, the two galaxies will pass through each other, their shapes distorted by gravity, their spiral arms stretched and torn apart. Over the course of 1 billion years, they will merge into a single massive elliptical galaxy. Astronomers have already given this future galaxy a name, Milkomeda, or alternatively, Milkomeda. By the time this happens, the Sun will have evolved into a red giant, and Earth, if it still exists, will be a charred and lifeless cinder. But the collision itself will be one of the most spectacular events in the history of the local universe. The Milky Way is also astonishingly crowded. Current estimates suggest that it contains between 100 billion and 400 billion stars. The exact number is difficult to determine because many stars are hidden behind vast clouds of interstellar dust, and others are too faint to detect even with our most powerful telescopes. But if we assume a middle estimate of roughly 200 billion stars, that means the Milky Way contains more stars than there are grains of sand on all the beaches of Earth, and orbiting those stars are planets. Lots of them. Conservative estimates suggest there are at least 100 billion planets in the Milky Way, and possibly many more. Among those planets, scientists estimate that as many as 300 million could be located in the habitable zone of their parent stars, the region where temperatures are just right for liquid water to exist on a planetary surface. Liquid water is considered essential for life as we know it. This means that within our galaxy alone, there could be hundreds of millions of worlds with the potential to host life. Some may be barren and lifeless. Others may harbour simple microbial organisms, and a few, perhaps, may be home to intelligent civilizations, looking up at their own night skies and wondering, just as we do, whether they are alone in the universe. With a sense of the Milky Way's astonishing scale and the remarkable phenomena it contains, we can now examine its fundamental characteristics in detail. Think of this as the galaxy's identity card, a comprehensive profile that defines what kind of galaxy we live in, how massive it is, where it sits in space, and what lies at its heart. Every galaxy in the universe can be classified and catalogued, and the Milky Way is no exception. Understanding its vital statistics helps us place our cosmic home in the broader context of the universe. The Milky Way is classified as a barred spiral galaxy. This classification tells us two important things about its structure. First, it is a spiral galaxy, meaning it has elegant curved arms that wind outward from a central region, like a cosmic pinwheel frozen in slow rotation. These spiral arms are not solid structures. They are density waves, regions where stars, gas and dust temporarily bunch together as they orbit the galactic center. As material moves into a spiral arm, it slows down slightly, creating a traffic jam of stars and gas. New stars form in these dense regions, lighting up the arms with brilliant blue and white stars. As the stars age and the density wave moves on, the arm appears to shift position even though the individual stars continue their orbits. Second, the term barred indicates that the galaxy has a linear bar-shaped structure running through its core. This bar is composed of densely packed stars and acts as a cosmic conveyor belt, funneling gas from the outer regions of the galaxy into the center, where it can fuel star formation and feed the supermassive black hole lurking there. The size of the Milky Way has been a matter of ongoing scientific debate and revision. For decades, astronomers believed the galaxy measured approximately 100,000 light-years across. But as observational techniques improved and telescopes became more sensitive, that estimate has grown. The problem is that galaxies do not have sharp edges. They do not simply stop at a defined boundary. Instead, they fade gradually into the darkness of intergalactic space. The outermost stars and globular clusters are so faint and so far from the galactic center that detecting them is extraordinarily difficult. Current estimates suggest the Milky Way could be as large as 150,000 light-years in diameter, and some studies have pushed that figure even higher, possibly exceeding 200,000 light-years when you account for the faint halo of stars and dark matter that surrounds the visible disk. This makes the Milky Way significantly larger than previously thought, though still modest compared to the true giants of the universe. The mass of the Milky Way is equally staggering. When astronomers talk about galactic mass, they often use the Sun as a reference point. One solar mass is the mass of our Sun, roughly 2 × 10⁻30 kilograms. The Milky Way contains approximately 1.5 trillion solar masses. That number is almost incomprehensible. It includes the combined mass of all the stars, planets, gas clouds, dust particles, black holes, neutron stars, and everything else we can detect. But remember, 90% of that mass is dark matter. Only about 10% is the ordinary matter we can see and study directly. Without dark matter, the Milky Way would be far less massive, and its gravitational pull would be insufficient to hold it together at the speed it rotates. When you look up at the Milky Way in the night sky, the brightest and most prominent section appears in the constellation Sagittarius. This is not a coincidence. Sagittarius lies in the direction of the galactic center, the heart of the Milky Way. When we gaze towards Sagittarius, we are looking through the densest concentration of stars in the galaxy, peering deep into the core region where billions of stars orbit a supermassive black hole. That black hole is called Sagittarius A star, and it is one of the most important objects in the galaxy. With a mass approximately 4 million times that of the Sun, Sagittarius A star sits at the exact gravitational center of the Milky Way, anchoring the entire structure. Every star in the galaxy, including our Sun, orbits this central point. The black hole itself is dormant at the moment, not actively consuming large amounts of matter, but in the past it was likely far more violent, devouring gas and stars and spewing enormous jets of energy into space. Our solar system is located far from this chaotic center. The Sun resides approximately 27,000 light-years from the galactic core, about halfway out toward the edge of the visible disk. We are not in the main body of a spiral arm, but rather in a smaller offshoot, called the Orion Arm, also known as the Orion Spur. This is a minor arm, a branch connecting two of the larger spiral structures. The Orion Arm is a relatively quiet neighborhood by galactic standards, far from the intense radiation and violent supernova explosions that are more common in the densely packed spiral arms. This quiet location may have been essential for the development of life on Earth. Too close to the galactic center, and the radiation environment would be hostile. Too far out, and there might not be enough heavy elements to form rocky planets. Our position strikes a balance, a safe harbor in the vast and sometimes violent galaxy. This location also reinforces an important truth. Humanity is not special. We are not at the center of the solar system. Earth orbits the Sun. We are not at the center of the galaxy. The Sun orbits the galactic core. We are not even in a prominent spiral arm. We occupy a small spur on the outskirts of a medium-sized galaxy in an unremarkable region of the universe. This realization, sometimes called the Copernican principle, has been one of the great humbling lessons of astronomy. Every time we thought we were at the center of things, we discovered we were not. And yet this ordinariness is also strangely comforting. It suggests that if life can arise here, in this average location around an average star in an average galaxy, then perhaps life is common throughout the cosmos. The Milky Way is not an isolated island drifting alone in the dark. It lives in a neighborhood, a gravitational community of galaxies that move, interact, and slowly reshape one another over billions of years. To understand our galaxy fully, it is not enough to look inward at its stars and gas. We must also look outward at the company it keeps and the vast structures of which it is a part. Astronomers call this community the local group. It is a collection of more than 50 galaxies bound together by their mutual gravity, spread across a region roughly 10 million light-years in diameter. The overall arrangement has a roughly dumbbell-like shape. At one end sits the Milky Way with its retinue of smaller satellites. At the other end lies the Andromeda galaxy, slightly larger and at least as massive, with its own swarm of companions. Between and around these two dominant galaxies are many smaller systems, from modest spirals to tiny dwarf galaxies, barely large enough to be called galaxies at all. The center of mass of the local group lies somewhere in the space between the Milky Way and Andromeda, a reminder that our galaxy is not the sole anchor of this neighborhood. Within the local group, 3 large spiral galaxies stand out. Andromeda, also known as M31, is the most massive and luminous, a grand spiral that will one day merge with the Milky Way. Our own galaxy, while slightly smaller in visible extent, likely rivals Andromeda in total mass once dark matter is included. The third major player is the Triangulum galaxy, M33, a smaller spiral that orbits near Andromeda and may itself be a satellite or close associate of that larger system. Around these giants swarm dozens of dwarf galaxies. Some are irregular in shape, others are spheroidal, and many are extremely faint. Their distribution, especially when viewed in 3 dimensions, reveals the underlying gravitational scaffolding of the group. The Milky Way is orbited by its own collection of satellite galaxies. Until the late 20th century, astronomers knew of only about a dozen such companions, including the more prominent dwarf spheroidals like the Sagittarius dwarf and the Fornax dwarf. As surveys have improved, Particularly with digital sky mapping and deep imaging, that number has grown dramatically. Today, there are at least 60 confirmed or strongly suspected satellite galaxies within roughly 1.5 million light-years of the Milky Way, with new ultra-faint dwarfs still being discovered. These satellites range from systems with millions of stars to tiny galaxies that contain only a few thousand stars, barely distinguishable from star clusters. Many are so diffuse and dim that they were invisible to earlier generations of telescopes. The two most famous of these companions are the large Magellanic Cloud and the small Magellanic Cloud. These are irregular dwarf galaxies visible to the unaided eye from the southern hemisphere as hazy patches of light near the southern sky. The large Magellanic Cloud is about 32,000 light-years across and contains roughly 1% of the Milky Way's mass. The small Magellanic Cloud is even smaller, about 7,000 light-years across. Despite their modest size compared to the Milky Way, both galaxies are astrophysical treasure troves. They host vigorous star-forming regions such as the Tarantula Nebula in the large Magellanic Cloud, the most active known stellar nursery in the entire local group. They also record a long history of gravitational interactions with each other and with the Milky Way, leaving behind tidal streams of gas and stars that arc across the sky as the Magellanic Stream. Beyond the well-known Magellanic Clouds, the Milky Way's satellite system includes a rich population of dwarf, spheroidal, and ultra-faint dwarf galaxies. These systems are of intense interest to cosmologists because they inhabit very low-mass dark matter halos. Their high ratio of dark matter to visible stars makes them ideal laboratories for testing theories of dark matter and galaxy formation. The discovery of new ultra-faint dwarfs, such as Aquarius 3 and Leo 6, continues to push the limits of how small and dim a galaxy can be, while still holding itself together with gravity. Future surveys, especially those conducted by next-generation observatories, are expected to reveal many more such satellites, filling out an intricate hierarchy of structures around the Milky Way. The local group itself does not exist in isolation. It is part of an even larger arrangement of galaxies known as the local sheet, and beyond that, the Laniakea supercluster, a vast gravitational basin that contains the Virgo cluster and many other groups and clusters spread across hundreds of millions of light-years. Our local group sits at the edge of a nearby low-density region called the local void, while surrounding it is a loose ring, or council of larger galaxies, that help define its broader environment. These structures are all embedded within the cosmic web, the immense network of filaments and voids formed by dark matter and gas on the largest scales. The Milky Way, its satellites, and the local group are just one small node in that web. Seen from this perspective, our galaxy is both ordinary and unique. It is ordinary in the sense that galaxies of similar mass and structure are common throughout the universe. A barred spiral with a few 100 billion stars orbiting within a group of a few dozen members is not unusual, but it is unique in the sense that this is our node in the cosmic network, the one place where we know life has arisen and begun to ask questions about its surroundings. The same gravitational forces that bind the local group together and shape the orbits of its galaxies will, over billions of years, also drive the eventual collision between the Milky Way and Andromeda. That future encounter, will not only transform the appearance of our galaxy, but will also reshape its local neighborhood, merging satellite systems, redistributing stars, and possibly triggering new waves of star formation. As the story continues, attention will turn inward again to the motion of our own sun within this wider context. The solar system is not fixed in place. It rides along in the galactic disk, orbiting the center of the Milky Way, even as the galaxy itself moves through the local group and the larger supercluster. Understanding that motion and the timescales involved gives a different sense of what it means to live in a galaxy that is both our home and just one participant in a much larger cosmic dance. We step beyond the Milky Way itself and examine the local group, the collection of more than 50 galaxies bound together by gravity into a dumbbell-shaped structure, dominated by the Milky Way and Andromeda. But now it is time to pull back inward and ask a question that affects us directly. What is the motion of our own solar system within this enormous galactic structure? How fast are we moving, and how long does it take to complete a single circuit around the galactic center? The answer is both humbling and difficult to grasp. The sun and everything that orbits it is not stationary. It is traveling through space at an extraordinary speed. The entire solar system moves around the center of the Milky Way at approximately 800,000 kilometers per hour. To put that into perspective, the fastest spacecraft humanity has ever built, the Parker Solar Probe, reaches speeds of around 700,000 kilometers per hour. At its closest approach to the Sun, our entire planetary system, including Earth, Mars, Jupiter, Saturn, and everything in between, is moving through the galaxy even faster than that, all the time, every second of every day. We do not feel this motion because everything around us, the air, the ground, the moon, and all the stars visible in the night sky, is moving along with us. But relative to the galactic center, we are racing through space. This motion is not random wandering. The sun follows an orbit around the center of the Milky Way, much as Earth orbits the sun and the moon orbits Earth. The gravitational pull of the hundreds of billions of stars, the interstellar gas, and especially the dark matter halo that surrounds the galaxy, all combine to keep the solar system bound in this enormous loop. The sun resides approximately 27,000 light-years from the galactic core, placing it roughly halfway between the center and the outer edge of the visible disk. At that distance, moving at 800,000 kilometers per hour, the sun takes an immense amount of time to complete a single orbit. One full circuit around the Milky Way requires between 225 million and 250 million Earth years. Astronomers call this period a galactic year, a cosmic timescale so vast that it dwarfs anything in human history, or even the history of most life on Earth. To understand what a galactic year really means, consider what has happened on our planet during that span of time. 230 million years ago, Earth was a very different world. Dinosaurs had not yet appeared. Instead, the planet was dominated by early reptiles, amphibians, and the last survivors of the Great Permian extinction. The supercontinent Pangaea was just beginning to take shape, and the climate was warm and dry over much of the globe. Since that time, the Sun has completed exactly one orbit around the Milky Way. During that single galactic year, the continents drifted apart, the dinosaurs rose and fell, mammals diversified, and eventually humans appeared and built civilizations. All of recorded human history, from the earliest writing to the present day, represents less than 1/150,000th of a galactic year. The Sun has not been sitting still since it formed. 4.6 billion years ago, a cloud of gas and dust collapsed under its own gravity, igniting nuclear fusion and giving birth to the Sun and its surrounding planetary disk. Since that moment, the Sun has been orbiting the galaxy continuously. Astronomers estimate that it has completed approximately 20 orbits during its lifetime. That means the Sun has travelled around the entire Milky Way 20 times, threading its way through spiral arms, passing above and below the galactic plane, and traversing distances measured in hundreds of thousands of light years. And yet, from our perspective, nothing has changed. The stars in the night sky appear fixed. The constellations remain the same from generation to generation. This stability is an illusion produced by the vast distances between stars. Even over millions of years, the shapes of the constellations shift only slightly, but the Sun's orbit is not a perfect circle. Like the orbits of planets around stars, it is slightly elliptical, and it is perturbed by the gravitational influence of spiral arms, molecular clouds, and other massive structures within the galaxy. The solar system also oscillates up and down relative to the plane of the galactic disk as it orbits. The Milky Way's disk is not a perfectly flat structure. It has thickness, and the Sun periodically crosses through the midplane as it moves. These crossings occur roughly every 30 to 40 million years, and some researchers have speculated that they might correlate with certain geological or biological events on Earth, such as increased meteor impacts or extinction events. However, these correlations remain debated and are not firmly established. The galaxy itself is not stationary either. Just as the Sun orbits the galactic center, the Milky Way as a whole is moving through space. It is part of the local group, and the entire local group is falling toward the Virgo cluster, a much larger collection of galaxies located about 50 million light-years away. Beyond that, the Virgo cluster and the local group are both part of an even larger structure called the Laniakea supercluster, a gravitational basin containing more than 100,000 galaxies. The center of mass of Laniakea lies in the direction of the constellation Centaurus, and our entire region of space is slowly drifting in that direction. These motions are layered on top of one another, like nested wheels within wheels, each governed by the same fundamental force of gravity, operating on different scales. In addition to its orbital motion, the Sun is also moving relative to the nearby stars in the solar neighborhood. This local motion carries the solar system through a region of space known as the local bubble, a cavity carved out by ancient supernova explosions. The Sun entered the local bubble several million years ago, and will remain within it for millions of years to come. The interstellar environment within this bubble is slightly less dense than average, offering the solar system a relatively benign cosmic environment compared to denser star-forming regions where radiation and stellar winds are more intense. Understanding the Sun's journey through the galaxy also helps astronomers trace the history of the solar system. By reconstructing where the Sun was at different points in its orbit, scientists can estimate when and where it passed through spiral arms or dense molecular clouds. These encounters could have had consequences for the formation and evolution of the Oort cloud, the distant reservoir of comets surrounding the solar system. Gravitational perturbations from passing stars or giant molecular clouds could have sent comets plunging into the inner solar system, potentially impacting planets and moons. Some researchers have even suggested that such events could have influenced the delivery of water and organic molecules to the young Earth, playing a role in the emergence of life. The concept of a galactic year also provides a useful perspective on the lifespan of the Sun itself. The Sun is currently about 4.6 billion years old, meaning it has completed roughly 20 galactic orbits so far. It is expected to remain a stable, hydrogen-burning star for another 5 billion years or so, before it exhausts the hydrogen in its core and begins to swell into a red giant. By that time, it will have completed an additional 20 to 22 orbits, bringing its total to around 40 or 42 trips around the galaxy. In that sense, the Sun is not quite halfway through its main sequence lifetime, and it is also not quite halfway through its total number of galactic journeys. Having established our place within the galaxy and our motion through it, the disk, the spiral arms, the central bar, the bulge, and the halo are all distinct components, each with its own history, composition, and role in the ongoing evolution of the Milky Way. Understanding these regions is essential to understanding how galaxies like ours form, grow, and change over billions of years. A galaxy is not a formless swarm of stars. It has structure, organization, and distinct components that reflect both its formation history and its ongoing evolution. The Milky Way is a barred spiral galaxy, and understanding what that means requires looking at each of its structural elements in turn. The defining feature of a barred spiral is the presence of a prominent bar-shaped structure running through the galactic center. This bar is not a solid object. It is a dense concentration of stars, gas, and dust that extends outward from the central bulge in a linear or slightly curved arrangement. The bar in the Milky Way measures roughly 27,000 light-years from end to end and rotates more slowly than the disk surrounding it. From Earth, we see the bar tilted at an angle of approximately 25 to 30 degrees, relative to the line connecting us to the galactic center. The bar is not merely decorative. It plays a crucial dynamical role by channeling gas from the outer regions of the galaxy inward toward the core. As gas clouds orbit within the disk, the gravitational influence of the bar deflects their paths, funneling material into the central regions where it can fuel bursts of star formation and feed the supermassive black hole at the galaxy's heart. Extending outward from the bar and the central bulge are the spiral arms, the graceful arcing structures that give spiral galaxies their characteristic appearance. The Milky Way has at least 2 major spiral arms and several smaller ones. The most prominent are the Scutum Centaurus arm and the Carina Sagittarius arm. These are not static structures etched permanently into the disk. Instead, they are density waves, regions where stars, gas, and dust temporarily accumulate as they orbit. As material enters a spiral arm, it slows down slightly due to the increased gravitational pull, creating a traffic jam. Massive young stars form in these dense regions, lighting up the arms with brilliant blue and white light. As the density wave moves on, those stars continue along their individual orbits, and the arm appears to shift position even though the stars themselves have not suddenly accelerated. In addition to the major arms, there are smaller features called spurs or minor arms. One of these is the Orion Arm, also known as the Orion Spur or Orion Cygnus Arm, which contains our solar system. The Orion Arm is located between the larger Perseus Arm and the Carina Sagittarius Arm. For many years, astronomers considered it a minor structure, a short bridge connecting two larger arms. However, more recent observations have suggested that the Orion Arm may be a significant feature in its own right, possibly a branch of the Perseus Arm, or even an independent spiral segment. The fact that we reside in this spur rather than in one of the major arms may be fortunate for the development of life. The major spiral arms are sites of intense star formation and frequent supernova explosions, environments where radiation levels can be hostile to complex biology. Our quieter location offers a more stable setting. The spiral arms themselves are not perfectly smooth or uniform. They twist, merge, and fragment. Some models suggest that the Milky Way may contain two overlapping spiral patterns, an inner pattern rotating more quickly and an outer pattern with tightly wound arms rotating more slowly. These patterns may be connected by bridging arms, creating a complex and dynamic structure. Observations in different wavelengths reveal different aspects of the arms. Optical images highlight young, hot stars. Infrared observations pierce through dust to reveal older stars and hidden star-forming regions. Radio maps trace the distribution of cold hydrogen gas, which outlines the spiral structure even in regions where stars are sparse. The disk of the Milky Way is not a single uniform sheet. It is divided into two components, the thin disk and the thick disk. The thin disk is where most of the galaxy's star formation occurs. It contains young stars, open star clusters, and the vast majority of the interstellar gas and dust. The thin disk has a vertical thickness of only a few hundred light-years, making it quite flat compared to its diameter of 150,000 light-years or more. Stars in the thin disk, including our Sun, follow relatively circular orbits around the galactic center and have low velocities perpendicular to the plane. The thick disk, by contrast, is composed of older stars with a much greater vertical extent. It reaches a scale height of roughly 600 to 1,000 kilometers above and below the midplane. Stars in the thick disk have less organized motion. Their orbits are more eccentric and more inclined relative to the plane. They also tend to have lower metal content than stars in the thin disk, indicating that they formed earlier in the galaxy's history when fewer generations of stars had lived and died to enrich the interstellar medium with heavy elements. Recent studies have identified stars in the thick disk that are surprisingly old, some exceeding 13 billion years in age, suggesting that the thick disk began forming much earlier than the thin disk. The distinction between the thin and thick disks is not always sharp. There is likely a smooth gradient in properties as one moves vertically away from the midplane. Some stars may have been born in the thin disk and later scattered into higher orbits by gravitational interactions with molecular clouds or spiral arms, blurring the boundary between the two populations. Understanding the relationship between the thin and thick disks is an active area of research, with implications for how galaxies assemble and evolve over cosmic time. The spiral arms and the bar do not rotate as a rigid body. Different parts of the disk orbit at different speeds, a phenomenon known as differential rotation. Stars closer to the galactic center complete their orbits more quickly than stars farther out. This differential rotation is what winds up the spiral arms and maintains the bar structure over billions of years. Without it, the arms would quickly become tightly coiled and lose their coherence. Instead, the density wave mechanism allows the spiral pattern to persist, even as individual stars and gas clouds move through it. It is a bit like the way traffic jams on a highway can remain in the same location even though individual cars are constantly entering and leaving the congested zone. The interplay between the bar, the spiral arms, and the disk is dynamic and complex. Gas flows along the arms, accumulates in the bar, and is funneled toward the center, where it can trigger starbursts or feed the central black hole. Stars form in the spiral arms, live out their lives, and eventually die, returning material to the interstellar medium. Over time, this cycle enriches the gas with heavy elements, changes the mass distribution within the disk, and influences the future evolution of the spiral pattern itself. The Milky Way is not a static snapshot, but a living, evolving system, shaped by the gravitational forces and physical processes that have been at work since its formation more than 13 billion years ago. In the next chapter, attention will focus inward toward the very heart of the Milky Way. The galactic center is a place of extremes, intense radiation, violent stellar dynamics, and the presence of Sagittarius A star, the supermassive black hole that anchors the entire galaxy. Understanding this central region is crucial to understanding the galaxy as a whole, for it is here that the most energetic processes unfold, and where the past and future of the Milky Way converge. In the previous chapter, we explored the architecture of the Milky Way, tracing the spiral arms that wind outward from the center and the bar that channels gas and stars through the core. Now we turn to the very heart of the galaxy, the galactic center, a region where density, energy, and gravity reach levels almost unimaginable compared to the quiet suburban neighborhood where the sun resides. This is a place defined by extremes, and understanding it is essential to understanding the Milky Way as a whole. The galactic center is located in the direction of the constellation Sagittarius, roughly 27,000 light-years from Earth. From our vantage point, it is hidden behind thick clouds of interstellar dust that absorb visible light, rendering the core invisible to optical telescopes. For centuries, astronomers could only guess what lay at the heart of the Milky Way. It was not until the development of infrared and radio astronomy in the 20th century that the veil began to lift. These longer wavelengths can pass through dust largely unimpeded, allowing astronomers to peer into regions that would otherwise remain dark. What they found was a dense concentration of stars, gas, and at the very center, a compact and incredibly massive object that would eventually be identified as a supermassive black hole. That black hole is known as Sagittarius A star, often abbreviated as A star in astronomical notation. It sits at the precise gravitational center of the Milky Way, anchoring the entire galaxy. The mass of Sagittarius A star has been determined through careful observation of stars orbiting it. By tracking the motions of individual stars over many years, astronomers can use Kepler's laws of orbital motion to calculate the mass of the object they are orbiting. The results are striking. Sagittarius, a star, has a mass of approximately 4.3 million times that of the Sun. That enormous mass is compressed into a region only about 12 million kilometers across, smaller than the orbit of Mercury around the Sun. Such a concentration of mass in such a small volume can only mean one thing. It is a black hole, a region of space where gravity is so strong that not even light can escape from within a certain radius known as the event horizon. The evidence for the existence of Sagittarius A star accumulated over decades. In the 1990s and early 2000s, teams led by astronomers Reinhard Genzel and Andrea Ghez independently monitored stars in the immediate vicinity of the galactic center using infrared telescopes. One star in particular, designated S2, became a crucial probe. S2 follows an extremely elongated orbit that brings it very close to the black hole once every 16 years. By measuring the star's position and velocity at different points in its orbit, the teams were able to determine the mass of the central object with high precision. In 2008, they announced that the mass was 4.3 million solar masses, providing what Genzel called the best empirical evidence that supermassive black holes do really exist. This work was later recognized with the Nobel Prize in Physics in 2020. Sagittarius A star is not currently in an active phase. It is not consuming large amounts of material, and as a result, it does not produce the brilliant jets and intense radiation seen in more active galactic nuclei. However, it is not entirely dormant. Gas and dust occasionally fall into the black hole, heating up and emitting X-rays and other forms of radiation as they spiral inward. These brief flares offer glimpses of the processes at work near the event horizon. The black hole is also surrounded by a population of stars unlike any found elsewhere in the galaxy. Some of these stars orbit the black hole at speeds exceeding a significant fraction of the speed of light, driven by the immense gravitational pull. Other objects in the region remain enigmatic, possibly disrupted stars or exotic compact remnants that have somehow survived in this hostile environment. The region around Sagittarius A star is extraordinarily dense. Within a few light years of the black hole, there are millions of stars packed into a volume that, in our local neighborhood, would contain only a handful of systems. This high density leads to frequent close encounters between stars, gravitational interactions that can alter orbits, strip away stellar companions, or even lead to collisions. The stars in this innermost region are also predominantly old and metal-poor compared to the stars in the disk. This suggests that the central bulge formed early in the history of the galaxy, during an era when the interstellar medium had not yet been enriched with heavy elements by successive generations of stars. The galactic center is also a site of intense magnetic fields and complex plasma dynamics. Radio observations have revealed intricate filamentary structures extending outward from the core, likely shaped by the interaction of magnetic fields with hot ionized gas. These structures are not fully understood, but they provide evidence of energetic processes that continue to shape the environment around the black hole, even in its current relatively quiet state. In the past, Sagittarius A star may have been far more active. Observing the galactic center remains a challenge despite advances in technology. The dust that obscures the core in visible light also affects observations at other wavelengths, though to a lesser degree. Infrared telescopes on the ground and in space have been able to resolve individual stars in the crowded central region, tracking their motions and measuring their properties. Radio telescopes have mapped the distribution of gas and detected the compact radio source associated with Sagittarius A star itself. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star, a historic achievement that showed the shadow of the black hole surrounded by a glowing ring of hot material. This image, constructed from observations by a network of radio telescopes spanning the globe, confirmed theoretical predictions about the appearance of a black hole and provided new tests of general relativity in the strong field regime. The galactic center is not just a curiosity for astronomers. It is the gravitational anchor of the entire Milky Way. Every star in the galaxy, including our Sun, orbits around this point. The mass of the central black hole, combined with the mass of the surrounding stars, gas, and dark matter, determines the orbital velocities and dynamical structure of the galaxy as a whole. The bar channels material inward, feeding the black hole and fueling star formation in the central regions. Over billions of years, this interplay between the black hole, the bar, and the disk shapes the evolution of the galaxy. Understanding the galactic center is therefore not just about understanding one small region. It is about understanding the forces that have governed the Milky Way since its formation. The extreme environment near Sagittarius A star also offers a unique laboratory for studying physics in conditions that cannot be replicated anywhere else. The strong gravitational field near the black hole allows astronomers to test general relativity with unprecedented precision. The high star density provides opportunities to observe stellar collisions, tidal disruptions, and the formation of exotic compact objects. The interaction between the black hole and its surroundings sheds light on how supermassive black holes grow and influence their host galaxies. These observations have implications not just for the Milky Way, but for understanding galaxies throughout the universe. We will look beyond the immediate vicinity of the black hole to examine the larger structures surrounding the galactic center, including the bulge and the mysterious Fermi bubbles, giant lobes of high-energy emission that extend far above and below the galactic plane. These features provide clues to the history of activity in the galactic center and reveal that the Milky Way's past was far more violent than its present state might suggest. We now move outward slightly to examine the larger structures that surround the core. These regions, the bulge and the spherical halo, are among the oldest parts of the Milky Way. They formed in the early epochs of the galaxy's history and preserve clues about the conditions that prevailed billions of years ago when the first stars were igniting and the Milky Way was still taking shape. Together, they form a kind of fossil record, a chronicle written in the motions and compositions of ancient stars. The bulge is a dense concentration of stars located at the center of the galaxy, surrounding the black hole and extending outward several thousand light-years from the core. When viewed from a distance, the bulge appears as a bright, oval-shaped region that gives the Milky Way's inner structure a somewhat boxy or peanut-shaped appearance. This shape is not a random feature. It is the result of the bar structure that runs through the core. The bar is not confined to a flat plane. Its gravitational influence extends vertically, puffing up the central region and creating the distinctive bulge shape. The bulge contains billions of stars, mostly older systems that formed early in the galaxy's history. These stars orbit in complex, chaotic patterns, driven by the combined gravitational influence of the bar, the central black hole, and the surrounding disk. The stars within the bulge are predominantly old and metal-poor compared to those in the thin disk. Metal-poor in astronomical terms means that these stars contain relatively few elements, heavier than hydrogen and helium. This low metal content is a signature of their age. In the early universe, heavy elements had not yet been produced in large quantities. The first generation of stars formed from nearly pure hydrogen and helium left over from the Big Bang. As those stars lived and died, they forged heavier elements through nuclear fusion and scattered them into space when they exploded as supernovae. Subsequent generations of stars incorporated more and more of these heavy elements. By measuring the metal content of stars in the bulge, astronomers can infer when they formed and learn about the chemical history of the galaxy. Not all stars in the bulge are metal-poor. There is also a significant population of metal-rich stars, indicating that star formation in the bulge continued over an extended period. Some of these younger stars may have formed in place, while others may have migrated inward from the disk due to gravitational interactions with the bar or spiral arms. The bulge is therefore not a single homogeneous population. It is a complex mixture of stars with different ages, compositions and orbital histories, all shaped by the violent and chaotic dynamics of the galactic center. Surrounding the bulge and extending far beyond the disk is the galactic halo, a vast, roughly spherical region that contains some of the oldest structures in the Milky Way. The halo is sparsely populated compared to the disk and bulge. It does not contain much gas or dust, and star formation ceased there billions of years ago. What it does contain are ancient stars and globular clusters, dense spheres of hundreds of thousands or even millions of stars bound together by gravity. The Milky Way has more than 150 known globular clusters, and most of them orbit within the halo, tracing out vast elliptical paths that take them far from the galactic plane and then plunge them back through it. Globular clusters are among the oldest objects in the galaxy, with ages typically ranging from 10 to 13 billion years. They likely formed during the early stages of the Milky Way's assembly, when the galaxy was still a roughly spherical cloud of gas collapsing under its own gravity. As the collapse proceeded and rotation began to dominate, the gas flattened into a disk, but the stars that had already formed remained in their more spherical distribution, creating the halo we observe today. Because globular clusters are so old, they contain stars with very low metal content, similar to the oldest stars in the bulge. Studying these clusters allows astronomers to probe the conditions in the early universe and test models of stellar evolution over timescales comparable to the age of the cosmos. The halo also contains individual stars scattered between the clusters. These halo stars follow highly elliptical orbits that bring them swooping in toward the galactic center and then carry them back out into the distant reaches of the galaxy. Their motions are not organized like the orderly rotation of stars in the disk. Instead, they move in random directions, reflecting the chaotic conditions that prevailed during the galaxy's formation. The halo extends far beyond the visible disk, possibly stretching 100,000 light-years or more from the galactic center. Much of this outer halo is filled not with stars, but with dark matter, the invisible mass that holds the galaxy together and accounts for 90% of its total mass. Beyond the immediate vicinity of the galactic center, one of the most striking and mysterious features of the Milky Way is a pair of gigantic structures known as the Fermi bubbles. These are enormous lobes of high-energy gas and cosmic rays that extend above and below the galactic plane, reaching outward from the core like the wings of some cosmic butterfly. Each bubble is approximately 25,000 light-years tall, and the entire structure spans roughly 50,000 light-years from end to end, about half the diameter of the entire galaxy. The bubbles were discovered in 2010 by astronomers analyzing data from the Fermi Gamma Ray Space Telescope. They are invisible to the naked eye and cannot be seen in optical light, but they glow brightly in gamma rays, the most energetic form of electromagnetic radiation. The exact origin of the Fermi bubbles remains uncertain, but they are almost certainly connected to past activity in the galactic center. One possibility is that they were created by a massive outburst from Sagittarius A, the supermassive black hole at the core of the Milky Way. If the black hole consumed a large amount of gas or disrupted a star several million years ago, it could have ejected jets of energetic particles and radiation that inflated the bubbles and drove them outward into the halo. Another possibility is that the bubbles were created by a burst of intense star formation in the galactic center, with many massive stars exploding as supernovae over a relatively short period. These explosions could have collectively driven a powerful wind that swept gas and cosmic rays out of the disk and into the halo. Both scenarios suggest that the galactic center was far more active in the recent past than it is today. A reminder that galaxies are not static objects, but dynamic systems that evolve over time. The edges of the Fermi bubbles are remarkably sharp, less than 2 degrees wide in gamma-ray observations. This sharpness suggests that the structure formed relatively quickly, during a sudden and impulsive event, rather than a slow, gradual process. The energetic particles responsible for the gamma-ray emission have extraordinarily high energies, indicating that whatever created the bubbles was an exceptionally violent phenomenon. The discovery of the bubbles has sparked renewed interest in the history of the galactic center and the role that black holes and starbursts play in shaping the environments of galaxies. Similar structures have been observed in other galaxies, suggesting that such outbursts may be a common phase in galactic evolution. The bulge, the halo, and the Fermi bubbles all tell parts of the same story. The Milky Way is not a simple spiral disk with a black hole at its center. It is a layered structure built up over billions of years through a combination of gravitational collapse, star formation, mergers with smaller galaxies, and occasional violent outbursts from the core. The oldest stars in the halo and bulge preserve information about the galaxy's infancy. The globular clusters trace out the original distribution of matter before the disk formed. The Fermi bubbles provide evidence of recent activity that reshaped the inner regions. Together, these components form a complex, interconnected system that continues to evolve even now. In the next chapter, we will pull back further and examine the extended halo and its role in the larger story of the Milky Way. The halo is not just a spherical shell of old stars and globular clusters. It is also the domain of dark matter, the invisible scaffolding that holds the galaxy together and extends far beyond the visible components. Understanding the halo is essential to understanding the total mass of the galaxy and its place within the larger cosmic web. We return to a structure briefly mentioned earlier, but deserving far deeper attention: the Fermi bubbles, two gigantic lobes of hot gas and cosmic rays that tower above and below the galactic plane, are among the most remarkable and mysterious features of our galaxy. Their discovery reshaped our understanding of the Milky Way's recent history and revealed that the galactic center has been far more active than previously imagined. The Fermi bubbles were discovered in 2010 by a team of astronomers analyzing data from NASA's Fermi Gamma Ray Space Telescope. The telescope had been scanning the entire sky in gamma rays, the most energetic form of electromagnetic radiation, mapping the diffuse glow of the Milky Way and cataloguing distant sources such as pulsars and quasars. But when astronomers processed the data carefully, removing foreground sources and the general background emission, an unexpected structure emerged. Two enormous lobes, extending symmetrically above and below the galactic center, glowing brightly in gamma rays. Each lobe measures approximately 25,000 light-years from the galactic plane to its outer edge, meaning the entire structure spans roughly 50,000 light-years from end to end. That is roughly half the diameter of the entire Milky Way. The bubbles are not visible to the naked eye or in optical telescopes. They emit very little light in visible wavelengths. Instead, they shine in gamma rays and, as later observations revealed, also in X-rays. The gamma rays are produced when highly energetic electrons moving at nearly the speed of light collide with lower energy photons, boosting them up to gamma ray energies in a process called inverse Compton scattering. The sheer energy required to accelerate electrons to such speeds and the vast scale of the structure indicate that the bubbles were created by an extraordinarily violent event. One of the most striking features of the Fermi bubbles is the sharpness of their edges. In the processed gamma-ray data, the boundaries of the bubbles are remarkably well defined, less than 2 degrees wide in angular extent. This sharp edge suggests that the bubbles formed quickly, during a sudden and impulsive event rather than through a slow, gradual accumulation of material. The spectrum of the gamma-ray emission is also distinct from the general diffuse glow of the galaxy, with a much harder spectrum peaking at energies around 10 giga-electron volts. Astronomers estimate that the electrons responsible for this emission must have energies exceeding 500 giga-electron volts. These are extraordinarily high energies, comparable to those produced in powerful particle accelerators on Earth, but occurring naturally in space on scales thousands of light-years across. The origin of the Fermi bubbles has been the subject of intense debate since their discovery. Two main hypotheses have emerged, each with its own strengths and challenges. The first proposes that the bubbles were created by a violent outburst from Sagittarius, a star, the supermassive black hole at the center of the Milky Way. Although the black hole is relatively quiet today, it may have been far more active in the recent past. If a large amount of gas, or even an entire star, fell into the black hole several million years ago, the resulting accretion could have triggered a powerful release of energy in the form of jets shooting out perpendicular to the galactic disk. These jets would have ploughed into the surrounding gas, sweeping it up and accelerating it outward, inflating the bubbles over a period of perhaps 100,000 years. Recent studies suggest that this outburst may have occurred approximately 2.6 million years ago, making the bubbles a relatively recent feature in the long history of the galaxy. The second hypothesis attributes the bubbles not to the black hole, but to a starburst, a sudden and intense episode of star formation in the galactic center. If a large amount of gas accumulated in the core and collapsed to form many massive stars over a short period, those stars would have lived fast and died young, exploding as supernovae within a few million years. The combined energy of thousands of supernovae, all concentrated in a small region, could have driven a powerful wind that carved out the bubbles much like the jets from a black hole. Both scenarios require an enormous release of energy, and distinguishing between them requires detailed modeling and comparison with observations at multiple wavelengths. Whatever their origin, the Fermi bubbles provide clear evidence that the galactic center experienced a dramatic and energetic event within the last few million years. This is a remarkably recent time by cosmic standards. When the bubbles were formed, early hominids were already walking the Earth. The light from the initial outburst, traveling at 300,000 kilometers per second, would have taken 27,000 years to reach the solar system. If our ancestors could have seen gamma rays, they would have witnessed a brilliant flare from the direction of Sagittarius as the event unfolded, though of course they had no telescopes or understanding of what they were observing. The bubbles themselves are now far from the galactic center, their material racing outward at speeds of millions of miles per hour. The discovery of the Fermi bubbles also led to the identification of a related structure in X-rays, observed by the eRosetta satellite in 2020. These eRosetta bubbles are even larger than the Fermi bubbles, extending to 80 degrees above and below the galactic plane. They overlap with the Fermi bubbles and are thought to be part of the same phenomenon, with the X-rays tracing slightly cooler and less energetic gas surrounding the hot gamma-ray emitting core. Together, the Fermi and eRosetta bubbles paint a picture of a galactic center that is anything but static. It is a dynamic, occasionally violent environment that shapes not only the core but also the surrounding halo and disk. More recently, astronomers have discovered even stranger structures within the Fermi bubbles. In 2025, observations revealed the presence of cold molecular clouds embedded within the hot plasma of the bubbles. These clouds, dubbed ice cube clouds because of their unexpected coldness, should not exist in such a hostile environment. The plasma in the Fermi bubbles reaches temperatures exceeding 1 million kelvins, nearly 2 million degrees Fahrenheit. Cold clouds with temperatures of only a few tens of degrees should have been destroyed almost immediately by the surrounding heat. Their survival suggests that they were much larger when they were first swept up by the outburst and have only now been eroded down to their current size. This discovery provides new constraints on the age of the Fermi bubbles and hints that the outburst may have occurred more recently than some earlier models suggested. The Fermi bubbles are not unique to the Milky Way. Similar structures have been observed in other galaxies, suggesting that such outbursts are a common phase in the life cycles of galaxies. When a supermassive black hole becomes active, or when a concentrated burst of star formation occurs, the resulting energy can reshape the surrounding environment on scales comparable to the size of the galaxy itself. These outbursts may play an important role in regulating star formation by expelling gas from the galactic center, preventing it from collapsing to form new stars. They may also enrich the halo and intergalactic medium with heavy elements, distributing the products of stellar nucleosynthesis far beyond the disk. The Fermi bubbles remind us that the Milky Way is not a serene, unchanging structure. It has a history, and that history includes violent, transformative events. In the next chapter, we will step back once more and examine the Milky Way's place in the larger universe, situating our galaxy within the hierarchy of cosmic structures that extends from the local group to the Virgo supercluster, the Laniakea supercluster, and beyond into the vast cosmic web. In the previous chapter, we explored the Fermi bubbles, the towering structures of hot gas and cosmic rays that reveal a violent past at the galactic center. Having now traced the Milky Way from its innermost core to the distant reaches of its halo, it is time to step back and view our galaxy not as an isolated entity, but as one component within a vast hierarchy of cosmic structures. The Milky Way exists within nested layers of organization, each larger than the last, extending outward from our local neighborhood to the very largest structures known in the observable universe. Begin with the familiar. The Sun resides in the Orion Arm, a minor spiral feature of the Milky Way located approximately 27,000 light-years from the galactic center. This is our immediate galactic neighborhood, a region of stars, gas, and dust orbiting together through the disk. The Orion Arm itself is situated between two larger spiral arms, the Perseus Arm and the Carina Sagittarius Arm, making it a relatively quiet and stable location compared to the more densely packed major arms, where star formation and supernova activity are more intense. From this vantage point, the rest of our cosmic address unfolds outward in scale, each level representing a new order of organization. The Milky Way, along with more than 50 other galaxies, belongs to a structure known as the local group. This is a gravitationally bound collection of galaxies spread across a region roughly 10 million light-years in diameter. The local group has a characteristic dumbbell shape, with the Milky Way and its satellites at one end and the Andromeda galaxy with its own retinue of companions at the other. Between these two dominant systems lie a number of smaller galaxies, including the Triangulum Galaxy and various dwarf galaxies. The center of mass of the local group lies somewhere between the Milky Way and Andromeda, roughly 450 kiloparsecs, or about 1.5 million light-years from our galaxy. The local group is itself a modest structure by cosmic standards, a small cluster of galaxies held together by mutual gravity, slowly evolving as the members orbit their common center of mass. The local group does not exist in isolation. It is situated on the outskirts of a much larger structure known as the Virgo supercluster. The Virgo supercluster is centered on the Virgo cluster, a massive concentration of more than 1,000 galaxies, located roughly 50 to 60 million light-years from the Milky Way. The gravitational influence of the Virgo cluster dominates the motions of galaxies across this region, including the local group. The Milky Way and its companions are slowly falling toward the Virgo cluster, drawn by its immense mass. This infall contributes to our overall motion through space, adding to the complex set of velocities that carry the Sun and its planets through the cosmos. For many years, astronomers considered the Virgo supercluster to be the largest structure to which the Milky Way belonged. But in 2014, that understanding changed dramatically. A team of astronomers led by Brent Tully used new methods to map the motions of galaxies in 3 dimensions, tracking not just their positions but also their velocities relative to the overall expansion of the universe. These peculiar velocities, the deviations from smooth expansion caused by gravitational attraction, revealed which galaxies were being pulled toward which gravitational centers. The analysis showed that the Virgo supercluster was not an independent structure, but rather one part of a much larger basin of attraction centered on a region known as the Great Attractor. This greater structure was named Laniakea, a Hawaiian word meaning immeasurable heaven or open skies. Laniakea is staggeringly vast. It spans approximately 500 million light-years in diameter and contains roughly 100,000 galaxies. The total mass of Laniakea is estimated at 10 to the power of 17 solar masses, 100 quadrillion times the mass of the Sun. The supercluster is divided into several subregions, including the Virgo supercluster, where the Milky Way resides, the Hydra Centaurus supercluster, which contains the Great Attractor, the Pavo-Indus supercluster, and the Southern supercluster. These subregions are connected by filaments and sheets of galaxies, structures that trace the underlying distribution of dark matter across hundreds of millions of light-years. The Milky Way lies at the edge of Laniakea, near the boundary of a low-density region called the local void. Voids are enormous regions of space containing very few galaxies, surrounded by denser walls and filaments. The local void is one such emptiness, a cosmic desert that helps define the edges of the Laniakea structure. Our location on the fringe of Laniakea, perched at the edge of a void, is not central or privileged. It is typical of the distribution of galaxies throughout the universe, where most systems reside along filaments and sheets, surrounding empty regions rather than in the cores of massive clusters. But even Laniakea is not the end of the hierarchy. Laniakea itself is being pulled toward an even larger concentration of galaxies, known as the Shapley supercluster, located several hundred million light-years away in the direction of the constellation Centaurus. The Shapley supercluster contains thousands of galaxies and exerts a gravitational influence across an enormous volume of space. Beyond Shapley, the structure continues. Laniakea and its surroundings are part of an even grander complex called the Pisces-Cetus supercluster complex, one of the largest known structures in the observable universe. These vast assemblages are part of the cosmic web, the overarching network of filaments, sheets, walls, and voids that characterizes the large-scale structure of the universe. Understanding this hierarchy gives context to the Milky Way's place in the cosmos. Our galaxy is not at the center of anything. It is not located in a massive cluster or at the heart of a supercluster. Instead, it occupies a relatively quiet position at the edge of a larger structure, orbiting within the local group, falling slowly toward the Virgo cluster, embedded within Laniakea, which itself is being drawn toward Shapley and beyond. This nested arrangement reflects the process by which the universe evolved from nearly uniform conditions shortly after the Big Bang to the highly structured distribution of matter we observe today. Tiny fluctuations in density, amplified by gravity over billions of years, grew into galaxies, clusters, superclusters, and the cosmic web itself. Our cosmic address can therefore be written as follows: Earth, the third planet of the solar system. The solar system, orbiting within the Orion Arm. The Orion Arm, part of the Milky Way galaxy. The Milky Way, a member of the local group. The local group within the Virgo supercluster. The Virgo supercluster, a subregion of Laniakea. Laniakea, part of the Pisces Cetus supercluster complex. And the Pisces Cetus supercluster complex, a small section of the observable universe, which extends roughly 46 billion light-years in every direction from Earth. Each level in this address represents an increase in scale by factors of hundreds, thousands, or millions, illustrating the extraordinary range of structures that fill the cosmos. Having explored the structure and history of the Milky Way, and having placed it within the larger cosmic landscape, we will now look ahead to what lies in store for our galaxy. The collision with Andromeda, predicted to occur in approximately 4 billion years, will fundamentally reshape the Milky Way and merge the two largest galaxies in the local group into a single massive elliptical system. This event represents the next major chapter in the life of our cosmic home. The Milky Way is not a static, unchanging structure. It is evolving, and its most dramatic transformation is yet to come. In approximately 4 to 4.5 billion years, the Milky Way will collide with the Andromeda galaxy, the largest spiral in the local group. This event will fundamentally reshape both galaxies and mark the beginning of a new chapter in the history of our cosmic neighborhood. The Andromeda galaxy, also known as Messier 31, is currently racing toward the Milky Way at a speed of roughly 110 kilometers per second, about 68 miles per second. This velocity was determined by measuring the blue shift of Andromeda's light. When an object moves toward us, the light waves it emits are compressed, shifting toward the blue end of the spectrum. The magnitude of this shift reveals the speed of approach. For decades, astronomers knew that Andromeda was approaching, but they were uncertain whether it would pass by harmlessly or collide directly. The answer required measuring not just the radial velocity, the speed toward or away from us, but also the tangential motion, the sideways drift across the sky. This is extraordinarily difficult because Andromeda is so far away that its motion across the sky is extremely small, less than 1/10 of a millisecond per year. The measurement was finally made in 2012 using the Hubble Space Telescope. Astronomers observed the positions of stars in Andromeda in 2002 and again in 2010, comparing them to the positions of distant background galaxies that serve as fixed reference points. By averaging over thousands of stars, they were able to determine the average proper motion with extraordinary precision. The result was clear. Andromeda's sideways velocity is very small, effectively negligible compared to its speed of approach. This means that the two galaxies are on a collision course. They will not pass by each other. They will merge. The collision will unfold over an immense time scale, roughly 1 billion years from the first encounter to the final settling of the merged system. The term collision is somewhat misleading. Galaxies are mostly empty space. The distances between individual stars are so vast that even when two galaxies pass through each other, the stars themselves almost never collide. If you could watch the event from a safe distance, you would see the two spiral disks approach, interpenetrate, and pass through one another, their shapes distorted by tidal forces as gravity stretches and twists the stars and gas. The galaxies would then swing back toward each other, pulled together by their mutual gravitational attraction. Over the course of multiple passes, they would lose energy and angular momentum, spiraling closer together until they finally merged into a single system. Despite the low probability of stellar collisions, the merger will be anything but gentle. The gravitational interactions between the two galaxies will fling stars into new orbits, scattering them into elongated, chaotic paths. Some stars will be ejected entirely, cast out into intergalactic space, as the galaxies exchange energy and momentum. Gas clouds within the two galaxies will collide, compressing and heating the material. This compression will trigger intense bursts of star formation, lighting up the combined system with brilliant blue supergiants and massive star clusters. The night sky from any surviving planet will be spectacular, filled with glowing nebulae, newly formed stars, and the distorted remnants of the two spiral structures merging into a chaotic, luminous mass. The Sun and the Solar System are likely to survive the collision relatively unscathed. The probability that the Sun will experience a close encounter with another star during the merger is extremely low. However, the Solar System's orbit within the galaxy will almost certainly change. The Sun currently resides about 27,000 light-years from the galactic center, orbiting in a relatively circular path. After the merger, it may be flung outward into the halo or pushed inward closer to the center, depending on the gravitational interactions it experiences during the chaotic dance of the two galaxies. From Earth, or whatever remains of it by that time, the view will be transformed. Andromeda, currently a faint smudge of light, visible only under dark skies, will grow larger and brighter over millions of years. Eventually it will dominate the night sky, a swirling disk of stars stretching across the heavens. The final product of the collision will be a single, massive galaxy, already nicknamed Milkomeda or Milkomeda. Simulations suggest that this merged galaxy will likely be a giant elliptical, a roughly spherical or football-shaped system with no distinct spiral arms or disk structure. Stars within Milkomeda will move on highly elongated, randomly oriented orbits, and the galaxy will possess little overall rotation compared to the orderly spin of a spiral disk. However, some simulations suggest alternative outcomes depending on how much gas remains in the two galaxies at the time of the merger. If sufficient gas is present, the merged system could form a new disk and become a lenticular or even a super-spiral galaxy. The central regions of Milkomeda are expected to have lower stellar density than typical elliptical galaxies today, because the Milky Way and Andromeda will have consumed most of their gas before the merger, leaving less material to fuel a central starburst. The collision will not be an isolated event. Other members of the local group, including the Triangulum Galaxy and various dwarf galaxies, will also be drawn into the merger over the following billions of years. Eventually, over a timescale of perhaps 150 billion years, most of the galaxies in the local group will coalesce into Milkomeda, completing the assembly of a single massive elliptical galaxy that will dominate this corner of the universe. By that time, the universe will have expanded so much that distant galaxies will have receded beyond the observable horizon, leaving Milkomeda isolated in a vast and nearly empty cosmos. There is an additional layer of irony to this future collision. By the time it occurs, the Sun will be nearing the end of its life as a main sequence star. 4 to 5 billion years from now, the Sun will have exhausted most of the hydrogen in its core and will begin to swell into a red giant, expanding to perhaps 100 times its current size and engulfing the inner planets, possibly including Earth. The collision of the Milky Way and Andromeda will therefore coincide, more or less, with the death of the Sun. Humanity, if it still exists in any recognizable form, will have had to leave the solar system long before the merger, either moving to other star systems or finding refuge on worlds orbiting younger, more stable stars. From that distant vantage point, they might witness the slow, majestic transformation of their ancestral galaxies into a single, unified structure. The Andromeda-Milky Way merger is a reminder that galaxies are not eternal, unchanging objects. They grow through accretion, merge with their neighbors, and evolve over billions of years. The Milky Way has already absorbed numerous smaller galaxies throughout its history, and it is currently in the process of consuming several dwarf galaxies, including the Sagittarius dwarf elliptical galaxy. The collision with Andromeda will be the largest and most dramatic merger the Milky Way has ever experienced. But it is not fundamentally different in kind from the smaller mergers that have shaped the galaxy throughout its existence. We looked ahead to the dramatic collision between the Milky Way and Andromeda, an event that will reshape both galaxies into a single massive elliptical system billions of years from now. But to understand the future, we must also understand the present inhabitants of the galaxy. The Milky Way is home to hundreds of billions of stars, and these stars come in a remarkable variety of types, each playing a different role in the ecology and evolution of the galaxy. Some are ancient and fading, others are young and brilliant, and still others have already died, leaving behind compact remnants or violent explosions. Understanding the stellar population of the Milky Way is essential to understanding the galaxy itself. The most common type of star in the Milky Way is the red dwarf. These are small, cool stars with masses between roughly 8% and 50% that of the Sun. Red dwarfs make up approximately 70 to 85% of all stars in the galaxy, meaning that the majority of the Milky Way's stellar population is composed of these dim, long-lived objects. Despite their numerical dominance, red dwarfs are difficult to observe because they are so faint. Most of them cannot be seen with the naked eye, even from dark locations. The nearest red dwarf to the Sun, Proxima Centauri, is only about 4 light-years away, yet it is invisible without a telescope. Red dwarfs owe their longevity to their extremely slow rate of nuclear fusion. Because they are so small and cool, the pressure and temperature in their cores are lower than in larger stars, and hydrogen is fused into helium at a much more leisurely pace. More importantly, red dwarfs are fully convective, meaning that material from the outer layers constantly circulates down into the core and back out again. This circulation ensures that fresh hydrogen is continually brought into the fusion zone, allowing the star to burn through a much larger fraction of its fuel than stars like the Sun, which have radiative cores where helium accumulates and eventually shuts down the fusion process. As a result, red dwarfs can live for hundreds of billions or even trillions of years. To put that in perspective, the universe itself is only about 13.8 billion years old. Every red dwarf that has ever formed is still burning today, and will continue burning for timescales vastly longer than the current age of the cosmos. This extraordinary longevity makes red dwarfs particularly interesting in the search for life beyond Earth. Although red dwarfs are cooler and dimmer than the Sun, their habitable zones, the regions where liquid water could exist on a planet's surface, lie much closer to the star. Planets in these zones receive the right amount of energy despite the star's faintness. Estimates suggest that there may be tens of billions of Earth-sized or super-Earth planets orbiting in the habitable zones of red dwarfs in the Milky Way alone. If life can arise and survive around these stars, then red dwarf systems could be the most common sites of biology in the galaxy. However, these systems also present challenges. Red dwarfs are known for their violent flares, sudden bursts of radiation and charged particles that could strip away a planet's atmosphere if the planet is too close or lacks a strong magnetic field. Despite these challenges, the sheer number of red dwarfs and the vast timescales over which life could evolve make them compelling targets for future exoplanet research. At the other end of the spectrum are stars like the Sun, medium-sized yellow dwarfs with masses roughly similar to our own star. These are less common than red dwarfs, making up only about 7% of the stellar population. Sun-like stars have lifetimes measured in billions rather than trillions of years. The Sun, for example, is approximately 4.6 billion years old and will remain on the main sequence, fusing hydrogen in its core, for another 5 billion years before it exhausts its fuel and begins to evolve into a red giant. These stars are important because they represent the class in which we know life has arisen at least once, and their moderate temperatures and relatively stable energy output make them favorable candidates for hosting habitable planets. Even rarer are the massive stars, those with many times the mass of the Sun. These giants shine with tremendous brightness and burn through their fuel at an astonishing rate. A star 20 or 30 times the mass of the Sun may live for only a few million years, a blink of an eye compared to the 10 billion year lifespan of a Sun-like star, or the trillions of years of a red dwarf. Massive stars are the engines of chemical enrichment in the galaxy. In their cores, they fuse not only hydrogen into helium, but also helium into carbon, carbon into oxygen, oxygen into neon, and so on up the periodic table, creating elements as heavy as iron through successive stages of fusion. When these stars exhaust their fuel, they explode as supernovae, scattering these newly forged elements into the interstellar medium, where they can be incorporated into new generations of stars and planets. Without massive stars, the universe would contain only hydrogen and helium. There would be no carbon, no oxygen, no nitrogen, and no heavy elements necessary for rocky planets and life as we know it. The remnants of dead stars also populate the galaxy. When a star like the Sun exhausts its fuel, it sheds its outer layers in a planetary nebula, leaving behind a dense core known as a white dwarf. White dwarfs are roughly the size of Earth, but contain about half the mass of the Sun, making them incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth. White dwarfs no longer undergo fusion. They simply radiate away their residual heat over billions of years, gradually fading into darkness. More massive stars do not have such a gentle end. When they explode as supernovae, their cores collapse into even denser objects. If the core has a mass between about 1.4 and 3 solar masses, it becomes a neutron star, a sphere only about 20 kilometers across but containing more mass than the Sun. Neutron stars are so dense that a teaspoon of neutron star material would weigh as much as a mountain. If the collapsing core is more massive still, not even neutron degeneracy pressure can support it. The core collapses into a black hole, a region where gravity is so strong that nothing can escape. The Milky Way contains millions of stellar mass black holes, the remnants of massive stars that have reached the ends of their lives. Most of these black holes are invisible, detectable only through their gravitational influence on nearby stars or gas. Occasionally, a black hole in a binary system will pull material from a companion star. As this gas spirals inward, it heats up to millions of degrees and emits intense X-rays, briefly revealing the black hole's presence. Black holes also play a role in the dynamic evolution of star clusters, as their gravitational interactions can eject other stars from the cluster or alter their orbits. The diversity of stellar types in the Milky Way reflects the ongoing cycle of birth, life, and death that has shaped the galaxy over billions of years. Red dwarfs, the quiet majority, will outlast all other stars, continuing to burn long after the Sun and every massive star in the galaxy have died. Sun-like stars, fewer in number but more luminous, represent the middle ground, stable enough to host life for billions of years. Massive stars, rare and short-lived, drive the chemical evolution of this galaxy and seed the interstellar medium with heavy elements. And the remnants, white dwarfs, neutron stars, and black holes, serve as the endpoints of stellar evolution, compact objects that preserve the memory of stars that once shone brightly. The star-forming regions of the Milky Way, concentrated in the spiral arms and dense molecular clouds, continue to produce new stars even today. Roughly 7 new stars are born in the galaxy every year on average. This rate has slowed over the history of the galaxy as gas is consumed and expelled, but it has not stopped. Star formation will continue for billions of years to come, though at a gradually declining rate, until the gas is exhausted or the merger with Andromeda reshapes the entire system. In the next chapter, we will explore the cultural and mythological significance of the Milky Way, examining how different civilizations have interpreted the glowing band in the sky and what it has meant to humanity throughout history. In the previous chapter, we explored the diverse stellar population of the Milky Way, from the long-lived red dwarfs that dominate the galaxy by number, to the massive stars that drive chemical evolution and the compact remnants left behind by stellar death. Now we shift our perspective once more, not to the science of the galaxy, but to its cultural significance. Long before astronomers understood the true nature of the Milky Way, human civilizations across the globe looked up at the glowing band in the night sky and wove stories, myths, and meanings into its light. The Milky Way has been a source of wonder, a guide for travelers, a sacred pathway, and a canvas for the imagination throughout human history. The name Milky Way itself comes from ancient Greek mythology. The Greeks called the glowing band across the sky galaxies, which means milky, derived from the Greek word for milk, gala. The myth explaining its origin centers on Heracles, the legendary hero and son of Zeus. According to one version of the story, Zeus wanted his son to gain immortality by drinking the milk of his wife Hera, the queen of the gods. While Hera was asleep, Zeus placed the infant Heracles at her breast to suckle. But Heracles drank so vigorously that Hera awoke in pain and pushed the child away. As she did so, her milk sprayed out across the heavens, creating the luminous trail of stars that would become known as the Milky Way. This myth gave the galaxy its name in Greek and later in Latin, where it became Via Lactea, the Milky Road, from which the English name is derived. The myth reflects a deeper connection between the heavens and the divine. For the ancient Greeks, the night sky was not merely a collection of distant lights, but a realm inhabited by gods, heroes, and mythological figures whose stories were written in the stars. The Milky Way served as a bridge between the mortal and divine worlds, a celestial river that carried meaning and narrative. This interpretation was not unique to Greece. Across the Mediterranean, the Romans inherited the Greek myth and incorporated it into their own traditions, identifying Hera with Juno and telling much the same story. The image of the Milky Way as spilled milk became one of the most enduring origin myths in Western culture, depicted in countless works of art, including paintings by Renaissance masters such as Jacopo Tintoretto, whose famous work captures the moment of Hera's milk streaming into the sky. In China, the Milky Way has been known for thousands of years as the Heavenly River or Silver River, a shimmering stream of stars that divides the sky. Chinese mythology associates the Milky Way with one of the most beloved and enduring love stories in East Asian culture, the tale of the Weaver Girl and the Cowherd, known as Ji Nu and Niu Lang. According to the legend, Ji Nu was the seventh daughter of the goddess of heaven, a skilled weaver who lived in the celestial realm. She fell in love with Niu Lang, a humble cowherd on earth. The two married and lived happily together, but their devotion to each other caused them to neglect their duties. Angered, the goddess of heaven separated them, placing them on opposite sides of the heavenly river so they could never meet. The couple's grief moved the magpies, who took pity on them and formed a bridge across the Milky Way with their wings once a year, on the 7th day of the 7th lunar month, allowing the lovers to reunite for a single night. This reunion is celebrated during the Qixi festival, often called the Chinese Valentine's Day. On this night, people gaze up at the stars Vega and Altair, which represent Ji Nu and Niu Lang, shining on opposite sides of the Milky Way. When the three stars, Vega, Altair, and Deneb, form a triangle in the summer sky, it is said that Deneb represents the bridge of magpies that allows the lovers to meet. If it rains on Qixi, the drops are said to be the tears of the separated couple. This story, known across China, Korea, Japan, and Vietnam, has shaped cultural traditions and festivals for centuries and continues to be celebrated today. In ancient Egypt, the Milky Way held profound cosmological significance. Egyptians referred to it as the winding waterway of the gods and saw it as a celestial counterpart to the Nile, the river that sustained all life in their civilization. Just as the Nile flowed through the land, bringing water and fertility, the Milky Way flowed through the heavens, carrying the souls of the dead and the gods themselves. The Milky Way was associated with the journey of Ra, the sun god, who travelled through the underworld each night before being reborn at dawn. It was also seen as a pathway for the deceased, a cosmic river along which souls travelled to the afterlife and the realm of the gods. The appearance of the Milky Way in the sky signalled the flooding of the Nile, an event critical to Egyptian agriculture. Farmers relied on this celestial guide to know when to plant and harvest, linking the rhythms of the heavens directly to survival on Earth. Across the Americas, indigenous cultures developed their own interpretations of the Milky Way. The Maya viewed it as the world tree when it aligned with the north-south axis, a sacred structure connecting the underworld, the earth, and the heavens. When aligned east-west, they saw it as a canoe carrying the maize god to the place of creation, reflecting their agricultural and cosmological beliefs. The Apache tradition interpreted the Milky Way as the path to the afterlife, a trail that crossed the shoulders of Yolkai-Naleen, the goddess of death, and along which all souls must travel after leaving the mortal world. These interpretations reveal a common theme. The Milky Way, regardless of culture, was often seen as a bridge, a path, or a river connecting different realms, whether between life and death, earth and sky, or the mortal and the divine. The appearance of the Milky Way in the night sky has also served practical purposes throughout human history. Before the invention of the compass and modern navigation, travelers, sailors, and nomads used the stars to find their way. The Milky Way, stretching across the sky in a predictable arc that changes position with the seasons, provided a reliable reference. In the southern hemisphere, where the galactic center is visible and the Milky Way appears brightest, indigenous Australians used the dark lanes within the luminous band, regions obscured by dust clouds, as markers and guides. These dark nebulae, shaped like animals and figures, formed constellations in their own right and played important roles in navigation, storytelling, and seasonal calendars. The Milky Way has also inspired questions about our place in the universe. For much of history, humans did not know what the glowing band actually was. Some philosophers speculated that it was a crack in the celestial sphere through which heavenly light shone. Others thought it was a reflection of earthly fires or a concentration of distant stars. It was not until Galileo turned his telescope toward the Milky Way in the early 17th century that the true nature began to reveal itself. He saw that the band was composed of countless individual stars, far too numerous and faint to be seen with the naked eye. This discovery marked the beginning of a profound shift in understanding, one that would eventually lead to the realization that we live within a vast galaxy, and that galaxy is just one among billions. The myths and stories woven around the Milky Way reflect humanity's deep need to find meaning in the cosmos. Whether seen as spilled milk, a river of stars, a bridge of magpies, or a pathway to the afterlife, the Milky Way has served as a mirror for human hopes, fears, and imaginations. These stories remind us that science and mythology are not opposites, but different ways of engaging with the same mystery. In the next chapter, we will address some of the most pressing scientific questions that remain about the Milky Way, exploring the frontiers of current research and the mysteries that continue to challenge astronomers. In the previous chapter, we explored the cultural and mythological significance of the Milky Way, examining how civilizations across the world interpreted the glowing band of stars and wove it into their stories, festivals, and spiritual beliefs. Now, in this final chapter, we return to the scientific frontier and address some of the most pressing unanswered questions about our galaxy. Despite centuries of observation and decades of sophisticated space missions, the Milky Way remains full of mysteries. Understanding these questions not only deepens our knowledge of our cosmic home, but also sheds light on fundamental aspects of the universe itself. Perhaps the most profound mystery surrounding the Milky Way is the nature of dark matter. As discussed earlier, dark matter accounts for roughly 90% of the total mass of the galaxy and provides the gravitational scaffolding that holds the visible structures together. Yet despite overwhelming evidence for its existence, scientists still do not know what dark matter is made of. It does not emit, absorb, or reflect light in any part of the electromagnetic spectrum. It interacts with ordinary matter almost exclusively through gravity. Decades of experimental effort have been devoted to detecting dark matter particles directly, using sensitive detectors buried deep underground to shield them from cosmic rays and other background radiation. So far, no experiment has produced a conclusive detection. The leading candidates for dark matter particles are weakly interacting massive particles, or WIMPs, theoretical particles that would have been produced in large quantities in the early universe and would interact only very weakly with ordinary matter. Other candidates include axions, sterile neutrinos, and primordial black holes. Each of these possibilities has its own theoretical motivation and predicted signature, but none has yet been confirmed. Recent studies have detected unusual gamma-ray emissions from the halo of the Milky Way that match the expected signature of dark matter annihilation, the process by which dark matter particles collide and convert into ordinary particles and energy. However, these signals are difficult to interpret because the astrophysical backgrounds are complex and uncertain. Other sources, such as pulsars or cosmic ray interactions, could produce similar signals. The question of what dark matter is remains one of the greatest unsolved problems in modern physics. Another major question concerns the formation and assembly history of the Milky Way. How did the galaxy come to have its current structure, with a disk, a bulge, a bar, and a halo? When and how did these components form, and how have they evolved over billions of years? The Gaia satellite, launched by the European Space Agency, has revolutionized our understanding of this history by measuring the precise positions, distances, and motions of more than 1 billion stars in the Milky Way. By tracing the orbits of stars backward in time and analyzing their chemical compositions, astronomers can identify groups of stars that formed together in the same environment and were later scattered or absorbed into the galaxy. One of the most spectacular discoveries from Gaia data is the identification of the Gaia Enceladus, or Gaia sausage merger, a collision between the early Milky Way and a fairly massive dwarf galaxy that occurred approximately 10 billion years ago. This merger was violent enough to disrupt the young disk of the Milky Way, heating the existing stars and scattering them into the thick disk and halo. It also contributed many globular clusters to the galaxy and may have triggered the formation of the bar. In fact, Gaia data suggests that roughly half of the Milky Way's globular clusters come from merger events rather than forming within the Milky Way itself. The discovery of Gaia Enceladus and other ancient mergers has shown that the Milky Way grew through galactic cannibalism, absorbing smaller galaxies over billions of years and incorporating their stars into its own structure. The detailed assembly history of the Milky Way is still being pieced together. Cosmological models predict that galaxies like the Milky Way are made up partly of stars that formed in situ within the galaxy itself, and partly of stars that formed in other smaller galaxies and were later accreted. Most of the more massive merger events should have occurred more than 9 or 10 billion years ago, during the early epochs of galaxy formation. The surviving satellite galaxies, such as the large and small Magellanic clouds and various dwarf galaxies, hold important clues to the properties of those early building blocks. Understanding how these smaller systems contributed to the Milky Way's growth helps astronomers reconstruct the broader history of galaxy formation in the universe. A third major question concerns the potential for life beyond Earth. How many habitable planets exist in the Milky Way, and how many of them might actually host life? The discovery of exoplanets, planets orbiting other stars, has accelerated dramatically in recent decades, thanks to missions like NASA's Kepler Space Telescope and the Transiting Exoplanet Survey satellite. Scientists now estimate that there are billions of planets in the Milky Way, and a significant fraction of them orbit within the habitable zones of their stars, the region where liquid water could exist on a planet's surface. One recent study estimated that roughly 1 in every 4 Sun-like stars has an Earth-sized planet in its habitable zone. With hundreds of billions of stars in the Milky Way, that translates to approximately 10 billion potentially habitable planets in the galaxy. This estimate includes planets around Sun-like stars, but it does not account for the far more numerous red dwarfs, which, as discussed earlier, may host tens of billions of additional habitable worlds. Recent research has also suggested that even white dwarf stars, the remnants of Sun-like stars, could potentially host habitable planets, further expanding the number of possible environments for life. However, the existence of habitable planets does not guarantee the presence of life. The conditions required for life to arise and survive are still not fully understood. Liquid water, stable temperatures, and a protective atmosphere are necessary, but perhaps not sufficient. The planet's distance from violent stellar flares, the presence of a magnetic field to shield against radiation, and the delivery of organic molecules through comets or asteroids may all play critical roles. Understanding how many of the billions of potentially habitable planets in the Milky Way actually host life, and whether any of that life is intelligent or technological, remains one of the most profound questions in science. The search for biosignatures in the atmospheres of exoplanets, using next-generation telescopes like the James Webb Space Telescope, is one of the most exciting frontiers in astronomy today. Other open questions include the exact rate of star formation in the Milky Way and how it has changed over time, the role of the bar in funneling gas to the galactic center and regulating star formation, the detailed structure and dynamics of the spiral arms, and the long-term fate of the galaxy beyond the merger with Andromeda. Each of these questions is the subject of active research, with new observations, simulations, and theoretical models continually refining our understanding. The Milky Way is not just a subject of academic curiosity. It is our cosmic home, the vast structure within which all of human history has unfolded. Every star you see in the night sky, every constellation that guided ancient travelers, every element in your body forged in stellar cores, all of it is part of the Milky Way. Understanding the galaxy is understanding ourselves, our origins, and our place in the universe. As technology advances and new missions explore the cosmos, the answers to these questions will reshape our view of the galaxy and the broader universe. The journey of discovery continues, and the story of the Milky Way is far from finished. The Milky Way has been a constant companion throughout human existence, a glowing river of stars that has inspired wonder, guided journeys, and sparked imaginations. From the myths of ancient Greece and China to the precise measurements of modern space telescopes, the galaxy has been a canvas for both poetry and science. As we look to the future, the Milky Way will continue to challenge us, to surprise us, and to remind us that we are part of something far larger and more ancient than ourselves. The quest to understand the Milky Way is, in many ways, the quest to understand the universe and our place within it.